The topic is nanofacturing. And we are team 2513. So that's the name of our team. And this is the team. So Joe and Bob, they have the technology that we're going to use to do this nanofacturing. Rachel has background in polymer. Me, Union, Professor Ito, and Liang, we are basically chemists or material scientists. We can do the...
Here, hold this up like that.
Okay. We can do material design, and we can also think about the application. We can do characterizations. Matthew is the expert. We can provide the computational support. We have Damian, can do force AFM, and we have Guillermo, right? I'm sorry. Correct me. Okay. It can also do synthesis. So this is the thing. What happened here? Okay, so yeah, it's fine here. So basically, we want to combine this state-of-the-art nanotechnology, which is not a science fiction. It's already available. Bob and Joe, they're expert. And we're going to use the wet chemistry. We're going to use surface chemistry. And we'll also chase the holy grail of making polycatinein. So that can be side product of our project. Also, we plan to combine the rotaction and catenin together to achieve our goal. And also, we'll talk about beyond molecule. We will talk about the macroscopic movement of 2D planes, more like pistons, you can call them. Also, these planes, they are dynamic. They will have restricted movement in XY plane. They will have precise movement in J direction, which is perpendicular to the plane. Also, we can use the technology like NAMES, so nano electromechanical system 2.0 maybe. It's already there, the market. So basically, this can be used to used for fabrication. And we can do several kind of applications like detection of molecules. You can use them for filter. We can from tunable nanoplasmonics, or we can tune the junction property between the two planes. We can do charge sensor. So this is how nanofacturing will work. So step-by-step process you can see here in this slide. So the first step is we'll take silicon substrate, and we'll basically create this atomically precise pattern using ultra-high vacuum. Yeah, this is too many things to do. Okay. So already too many things here, and there's like too many things in hand. Okay. So this step-by-step target, so we have silicon substrate, and we can basically prepare this precise pattern using this ultra-high vacuum techniques that is available. So these are the 2D array of the patterns you can see. Then we're going to install threads or poles with multiple station. We can have 2 or 3 stations, depend on what we want to do. We can do that using wet chemistry. Then we can basically decorate this station with ring-like molecules. So you can see the 2D representation here. So if I go from here, then this is the pattern in 2D way, and this is basically the 3D representation of this pole on the substrate. Then we are basically decorating this station with rings. You can see them in blue, and then we can add the threads, which are represented in red. So basically, this will be open-end threads, and since we can actually design this ring such a way that this thread will precisely sit the way we have shown here and form a mechanical interlocked molecular array. And then we basically tie these threads to complete this meme structure. And the ultimate goal is to have at least 2 planes. And each planes are basically a 2D catenin-like structure. And we have a station here, and depending on the stimuli, basically the distance between these 2 planes can be changed. And we can use this for the application. So here is the more details about the technology. So where does the precision comes from? This, of course, comes from the pattern generation with using the NAMES technology. So you can see we can actually achieve quite a bit precision here. You can see the scale bar is 1 nanometer. You can install the molecules. So these are the real data. So here they install a phthalocyanine molecule precisely. So definitely we'll have no trouble to make the 2D array. We can also detect the molecules. In this case, it's single molecules. And we can do the detection by monitoring the current level. You can see as when the molecule comes and sit here, you can see the change of the current level. So these are same details. So basically, this experiment also indicates the prospects of the sets, that is, what's that? The ACTs, single electron transistors. So here, I think the source and drains, and then you have a gate. You can detect even a quantum dot, which is sitting in the middle. And this is some more the patterns that I was talking. Maybe I should do more details. So this is the 2D array, and we're going to install this pole on this array by wet chemistry. And if you see, this one pole has kind of 3 stations, and we can basically modify the station with ring like this, and each ring will also have 4 different kind of recognition to grab this red thread, which basically can form this mechanically interlock structure after we tie the open ends. And then we'll have this ultimate structure. So you can see the substrate, which can be an active substrate, so that it can basically detect the moments of these 2D planes. So we'll have this free moment in J direction. We can manipulate the distance, and by doing so, we can change the property. What's happening here? Great. So I think I can just explain more. So basically, we have a substrate. We can use this cutting-edge technology to fabricate these 2D catenate kind of layers, and we can also change the distance between these 2 layers. We can use these 2 planes to catch molecules, and so that way we can use it as a sensor. We can have an active substrate that can be used for reading reading that the catching moment, whatever going on there. We can make a nanoplasmonic junction depending on what kind of modification we are doing on the 2D plane. We can use it for filter application. We can install or we can transfer these patterns on a soft surface, and we can incorporate into the body probably. And then we can do a lot of bioapplication. So it can be used for biomedicine, or you can imagine, basically. So it has a lot of potential. We are trying to basically build it. And if you see here, we can basically sorry for the trouble here, but this is already published from the Stoddart group, how we can make this kind of catenane. So using these, basically, we can actually, the same chemistry, we can make this kind of array. Yeah, so I think I'm done. I hope the message is already sent, so if you have questions.
Great,
yeah.
Okay, thank you very much. So if I could,
Yeah.
no, you stay here because you're going to answer questions.
Okay.
I need the other mic. So questions from the judges. So stay up here.
Yeah.
Actually, everyone can answer the questions.
Any trouble?
Oh, here
Yes.
No, the judges will ask questions now.
Oh.
The judges.
Who are
Here we
the
go.
judges? Yes.
They're over here.
Yeah.
What do you foresee as the technical risks, and what do you propose as a pathway to mitigate those risks?
Right, like what kind of risk you're talking about?
Throw that to your group.
Yeah,
You don't
yeah.
have to do all the work here.
So technological stuff. Yep.
Well, one of the risks is, my understanding is this type of array has never been made, this two-dimensional structure. It's a goal that Fraser's group has, and I'm sure others do. The approach here is to frustrate non-specific interactions that might create non-ring bindings or ring bindings that are not in that array. So tethering things to the posts. So the only things that can reach each other to react are the ones that are supposed to. And that, even with the statistics and the fluctuations in the systems, you still can't have non-specific interactions. So that's the how we intend to address what is a very high risk, because nobody's been able to make these things.
Also, this polycatinean structure, it's very difficult to make them. So with their technology, it's maybe possible to make those fundamental structure. We can also have this suspension, like we can manipulate the distance between the two planes. So by doing so, we can use this for various different applications, from sensors or anything like this. You can do nanoplasmonics. Yep.
And one more risk is that we can now make these things, but fairly slow, and so we have plans to make them 1,000 million times faster, but we're not absolutely sure we can achieve that, so that's a risk.
Other questions?
Yeah. For each SET, I think each SET is at the center of like couple of rings or something. How is the interaction or coupling between SETs, expected? Because I think one SET will be talking to the other, or of course technically you cannot feed an SET unless you have some wave or something like that. So how this will interact? Is it like the first four around it expecting to have most effect, or that a different algorithm they interact? Because if this will go some computing, you need to understand how you are going to access each one so that you can address each item. That's a simple question if I may ask.
So we've shown that we can make the SET of that sensitivity. That's already demonstrated. So we don't see that as a risk. We think we've already shown that we have that sensitivity over that range.
Okay.
And the SETs here are unlike any others. These are very, very tiny atom-defined, few nanometer footprint. They're not.
Okay.
They're not
Another thing,
previous.
I see it's 2D, so that's 2D, but you don't have any kind of course, I don't expect that to be defined, but in your vision, you can have a scaling like that's big, like a carpet, and size of it X by Y. It might be actually 2.5D, but let's go for the 2D. 2D is kind of like you have a limitation for the size, because as you go toward the edges, the signal propagation will be weak and the coupling will be smaller, so you have some issues with noise and temperature and all this.
So for the device, if you think about the device, we can basically cover the whole substrate using that technology, I think, right? How big you can make an array, maybe centimeter by centimeter or more? Yeah. So, yeah.
Any
I think it takes more time.
Any other questions from the judges? One more?
I have a million more, but I can ask just the one. So, I'm a little bit confused about this wet chemistry on the silicon, first of all. How is that going to be affecting the patterning that you're doing to begin with? You didn't disclose anything about what wet chemistry is going to happen. That's the number one. The number two is that you're talking about tunable plasmonic, and it's not clear to me what is the plasmonics that we are looking at here, and what type of behavior are we expecting, and what will be this applied to. So, very vague statements in terms of all the applications.
Right. We didn't explain, but just think about, we basically, so how we are trying to build it. So depending on the design of each ring and the whole chemical design in terms of structure, we can target different applications. So this is a general way of making this. And now, if we target separate application, then we have to modify this ring, but that is known, if you think about what kind of molecules you need to install, the junction.
So let me just add that it would have made your proposal stronger to have an example of such an application so that one can visualize that you really have thought about it deeply. Not
Right. So I can just answer that. Just think about the sensor, right? So we have, rather than using a passive substrate, we can use an active substrate, which can actually detect the movement of these two planes. Now, if you just imagine if these two planes catch specific molecules, of course, that will depend on the design. So then basically they will change the current level, and we can measure that using.
In what way is that different from current technology based on SPR?
We're sort of out of time.
And
No,
also, just one line I just want to say, like, since this is a molecular machines conference and the whole community knows how difficult it is to make a polycatenin, and with this scale, so it's not only just application, but huge fundamental points lying there in our design.
Okay, thank you so much. That was exciting. Thank you. Let's give them a hand.